Hi everyone, welcome to our next video for week 2, and we're going to talk briefly about contingency tables. Contingency tables provide a way of portraying data that makes calculating probabilities easier. So this is a way of organizing data in a way that makes it easier to interpret. We actually already used one in a previous example. It helps us determine conditional probabilities, and it displays sample values in relation to two different variables, eye color versus hair color, age group versus time spent on social media, that may be dependent or contingent on one another. So contingent means dependent, and we're looking at the table to determine if one variable depends on another. So for example, this contingency table has a sample of 73 17 and 18-year-olds, and we're looking at how many in each of those age groups has or does not have their driver's license. We can use this contingency table to figure out whether the age of the teenager depends on whether or not they have a driver's license, or whether driver's license depends on how old they are. We're going to do two examples really quick. So this first one says the table shows the number of athletes who stretched before exercising and how many injuries within the past year. Words are hard. And they ask us two questions. What is P athlete stretches before exercising? And what is P athlete stretches before exercising, given that they had no injury in the last year? So here's our data table. We're going to start with question A. What is the probability of the athlete stretching before exercising? So stretching before exercising would be the entire stretches row. So we're looking at athletes who stretch divided by all athletes in the sample. So 350 divided by 800. So P stretches is 350 over 800, or 0.4375. So a little less than half of all of the people sampled stretch before they exercise. PB asks what is the probability that they stretch before exercising, given that they had no injury in the last year. So we know stretches given no injury should be stretches and no injury divided by no injury. So stretches and no injury is where that row and column intersect. So 295 people sampled stretched and had no injury out of 800. And then for no injury, there were 514 people total who were not injured in the last year out of that sample of 800. So 295 divided by 800 divided by 514 divided by 800. So those divide by 800 parts are going to cancel, and we end up with 925 divided by 514, or 0.5739. And just like the examples that we saw in a previous video, you'll notice with the conditional probabilities, stretches, given no injury, that the top of that fraction comes from the stretches and no injury, the box the two had in common, and the bottom just becomes the total no injury, which is the 514. So you can bypass that double fraction by recognizing that we're pulling that stretches and no injury directly from the no injury total instead of from the whole population. Okay, so let's try another one really quick. The table below shows a random sample of 100 hikers and the areas of hiking they prefer. So it's sorted by gender and then coastline, lakes and streams, or mountain peaks where they like to hike. The first thing they ask us to do is complete the table. They've given us some information, but not all the information. So first thing I know, they told me I have a random sample of 100 hikers. So I know that bottom right box has to be 100. And that checks out because 45 plus 55 is 100. I also know in that first row, 18 plus 16 plus that box has to be 45. So I can work backwards and figure out that missing box was 11. Now I can add downward. On mountain peaks, 11 plus 14 is 25. And then along that bottom total row, now I can fill in that missing box. I know that missing box plus 41 plus 25 is 100. So that missing chunk must be 34. And then these two missing boxes, I'm subtracting the total from the women's box. So 34 minus 18 is 16, and 41 minus 16 is 25. So we know how all of the pieces of the table fit together, and we can use information from the total rows and columns to fill in the middle chunks. Okay, so now that we've got our completed table, Part B asks, are the events female and the coastline independent? So independent events have those three conditions, and we can check any one of them. Is the conditional probability equal to the probability of the event happening alone? Or is the and probability, A and B, equal to PA times PB? So I'm going to do that last one. Is PF and C equal to PF times PC? Because those are things I can easily pick off from the table. So PF and C, we look in the table. Female and coastline is 18 over 100. For the next one, I'm looking for all females, so that's 45 over 100. And then I'm looking for PC is all coastline, so that's 34 out of 100. To do the math, I'm checking that PF times PC, 45 times over 100 times 34 over 100, is equal to 18 over 100. 18 over 100 is 0.18, and 45 over 100 times 34 over 100 is 0.153. So these events are not independent. Okay, the next one says find the probability that a person is male given that the person prefers hiking near lakes and streams. So we know for conditional probabilities, male given lake or stream is the probability of both male and lake or stream divided by the probability of lake or stream. So M and L is that thing they have in common, the 25 box over 100. And then PL, probability of lakes and streams, is the lakes and streams total, 41 over 100. And those 100s are going to cancel, and we should end up with 25 over 41, which is 0.6098. Okay, so hopefully those examples were a good review of how to use those data tables. We now know they're called contingency tables. If you have any questions on what you saw or anything we've covered this week, feel free to contact me via email or text message. Otherwise, I'll see you in the next video.